Geometry can be pretty challenging, so I thought maybe I'd make a quick video to give you some support while we work through these questions, and hopefully this can be a good reference for you when you are referring back to this stuff later. So we're going to work through these 5 questions that are on the back, and the light is kind of dim despite the fact that the windows are open, so I'm going to just turn on this light. I'm sure that barely helped. All right, cool. So we're going to work through these questions. Let's start with question 1. All right, car accident. We got this substance, sodium azide, will decompose to form sodium metal and produce enough nitrogen gas to fill an airbag. Okay, so we're talking about an airbag. This is how airbags work. And the reaction is NaN3. It turns into some sodium and some nitrogen gas. Now, I want you to take special note of this note up here. It says that none of the reactions have been balanced. As a reminder that before we get started with a stoichiometry question, I'm going to zoom in a bit here, we're going to need to balance any reactions. So step 1, let's say step A, we want to balance. So we want to balance the reactions if possible. So we've got a sodium azide, and that goes to some sodium metal plus nitrogen gas. Now, I see I have the same number of sodiums on both sides, but I've got 3 nitrogens here and 2 nitrogens here. So what I'm going to do is, it looks like I've got too many nitrogens on this side, so I'm going to make another one here. But actually, what I need eventually is the least common multiple of 2 and 3 is 6. So I'm going to need 6 nitrogens in total here. I'm going to put 3 here. That gives us 3 nitrogens. Meaning I'm going to need a 2 here, because 2 times 3 is going to be 6. And so that gives me 6 nitrogens on this side and 6 nitrogens on this side. Now I've got 2 sodiums, 2 NAs. I need some number of NAs here, so I'm going to put a 2 here as well. That gives us the same number of sodiums. Okay, so there's a balanced reaction. All right, so next we're going to want to convert. So we're probably told something about one substance. No, let's read the rest of this question. All right, so what's the mass of solid sodium? What is the mass of solid sodium produced by this reaction if the airbag contained 7 grams of sodium azide? All right, so we're going to start with some information about sodium azide. Okay, so we've got 7 grams of sodium azide. Okay, and just like any question that involves stoichiometry, we're going to need to get to a mole bridge. Okay, so we can go from moles of one substance to moles of another substance using this ratio only after we've converted into moles. So we're going to need to convert this number of grams of sodium azide into moles of sodium azide. All right, so to do that, we'll use our periodic table, find the molar mass. It's 23 for sodium. Okay, so sodium of 23 grams per mole, actually 23.0, and 3 nitrogens will give us nitrogens 14.0, so that's 14, 28, 42.0 grams per mole. And in total, we get 65.0 grams per mole. Okay. So we'll multiply this out and use that molar mass. So we want units of moles, so we'll have 1 mole of sodium azide up top, and we're going to cancel that with the number of grams that are in a mole, which is 65.0 grams. Okay. And now we're going to convert units of sodium azide into units of sodium. Okay, and it's a 2-to-2 ratio. 2 moles of sodium azide produce 2 moles of sodium. So I want my 2 moles of sodium azide down here. So they're going to cancel out diagonally. I'm just going to cancel out these things that cancel out diagonally already. So this is grams of sodium azide. And moles of sodium azide also cancel out, giving us units of moles of sodium metal, solid sodium. All right, and those are in moles. Now, lastly, we're asked, actually, what is the mass of sodium, solid sodium? So we actually want to convert that into a mass. So we're going to finally take that molar mass of sodium and say, okay, 1 mole of sodium is going to give us 23.0 grams of sodium. And then our moles of sodium cancel out. Now, notice what I've done here is I've been including the name of the substance that we're using. And that's important because the name changes. We're talking about a different substance after this step. And so this helps us keep track of what information pertains to sodium azide and what information pertains to sodium. Okay, so now we'll grab a calculator. Get 7 times 2 times 23. And then we'll divide that by 65, and divide it by 2. And we get 2.476. Now, of course, we should only have 1 sig fig, and so we'll just round that to 2 grams of sodium metal. And I'm just indicating that's a solid there, because that's what metals are. Okay. So we'll try and keep to these steps, make sure we're balancing first, and then we convert. So we'll move on to step 2. Question 2. All right. So question 2 talks about Issa. And it says that she watched an episode of Breaking Bad. She wanted to make thermite, a very exothermic reaction to melt some things. And it says thermite is a substance that releases enough energy to melt many metals. And the reaction is as follows. So we get some aluminum, we mix it with iron 3 oxide, and we make solid metal, and aluminum oxide. We want to know how Issa is going to get aluminum for this reaction by grinding up 14.9 grams of aluminum in a pop can. And the question is, how much iron oxide? How much iron oxide does she need to weigh out to react with this aluminum? Okay, so this is going to be quite a similar question to the one we did in class today, where we were performing that really endothermic reaction, where we had one amount of a substance and we need to know how much we need to mix with it. And this is a very common chemistry problem. All right, so the first thing we're going to do is we're going to balance. Okay, so I'm going to write out the reaction. We've got an aluminum, and we've got some iron 2 oxide, 3 oxide, pardon me, that's rust, in case you're wondering. And then we've got iron and aluminum oxide. Okay, sorry, I was off the screen, so pardon me. All right, now we're going to balance these suckers out. So let's start with the thing that shows up the least. Well, everything only shows up once, so I can really start with anything. I'll start with aluminum. So there's aluminum, there's 1 aluminum here, but there's 2 on the right-hand side, so I'm going to put 2 here. So there's 2 aluminums on each side. Okay. Now irons, there's 2 on this side, so I've got 2 irons here. Now I've only got 1 here, so I'm going to put a 2. So now I've got 2 irons as well. Looks like I've got 3 oxygens on each side, so actually now I'm balanced. That was pretty painless. So this oxygens is 3. And we're done. All right, cool. Moving on. Now we're going to convert. So what do we know in this question? Well, we knew we had 14.9 grams of aluminum. So we're going to start with 14.9 grams of aluminum. And we want to know, find out some information about how much iron 3 oxide. And that's this guy here, in case you were wondering, iron 3. If I mix it with oxides, oops, not here, that's a 2 minus. I would need 2 iron 3s to balance out the charges from these 3 oxides, and that's why this is iron 3 oxide. All right, anyhow. So we've got 14.9 grams of aluminum. And again, we want to get a mole bridge going on. We want to find out how many moles of aluminum we have. So to do that, we'll use the molar mass of aluminum, which is 27.0 grams. So 1 mole of aluminum is the same thing as 27.0 grams of aluminum. Okay, and now we get to use our mole bridge. This is a 2-to-1 ratio. What this tells us is that 2 moles of aluminum react with 1 mole of iron 3 oxide. 2 moles aluminum react with 1 mole of iron 3 oxide. Alright, so the mass of aluminum and moles of aluminum cancel out, and then lastly we were asked how much yeast needs to weigh out of the iron 3 oxide. So now we know how many moles of iron 3 oxide we have, and we want to convert that to a mass. To do that we gotta find the molar mass of iron 3 oxide. So what's the molar mass of iron? 55.8. So 55.8. And there's 2 irons. So the molar mass. So the molar mass of iron 3 oxide is 2 times 55.8 and 3 times 16.0. And we're going to add those values together. So whatever 55.8 times 2 plus 3 times 16. And our calculator knows bed mass, so it should do this correctly. And we'll get 159.6 grams per mole. So that means for 1 mole of iron 2 oxide, we've got 159.6 grams of iron 3 oxide. Okay, lastly, moles of iron 3 oxide cancel out. And we'll just crunch these numbers. So we got 14.9 times 159.6, and then divided by 27. Divided by 2. That's okay, it's 44 grams. Oh, 44.0, I suppose, which have 3 sig figs here. 44.0 grams of iron 3 oxide. Okay. All right, let's see if we can finish off these questions here for my next parent-teacher interview. All right. So, question 3 asks us to take a look at yeast. They eat glucose, just like us, for energy, and they produce carbon dioxide as a byproduct, also like us. And this carbon dioxide is used to make bread rise. That's the bubbles. That's why we put yeast in it. Bubbles it up, and it produces this gas and makes bread rise. The total reaction is here, and we want to balance the reaction to determine the volume of oxygen at STP that yeast will require so that they can eat 403 grams of glucose. Okay. So start with balancing. So we're going to balance this reaction out. So we've got, so I'm actually going to do this really quickly because we've done this one in class. And we've done this one in class because this is my favorite reaction. This is cellular respiration. All right, so carbons, we got 6 carbons here, so we're going to need 6 carbons there. Hydrogens, we need 12 on the left-hand side, or have 12 on the left-hand side, so we need 12 here. So if there's 2 hydrogens in a water, we'll need 6 waters in total. And lastly, I'll let you count this on your own, but if you counted all the oxygens, that means we actually need we need 12 of these oxygen molecules in total. All right, great. So next step is we're going to convert. So we're going to start with 403 grams of glucose. And we're just going to write glue like that, rather than write out the chemical formula every time. All right, and I need to take this to the mole bridge, so I need to convert this into a number of moles. And so the molar mass of glucose is 180 grams per mole. So I'm just going to write that in here so you can find that on your own to confirm that. 1 mole of glucose is equal to 180 grams of glucose. Okay, and now what do we ask for? We actually ask for the volume of oxygen molecules. So it looks like that's a 1:6 ratio. For every 1 glucose molecule, 1 mole of glucose. For every 1 mole of glucose, you have to get 6 moles of oxygen. So we get 6 moles of O2. And now we're asked to find the volume of oxygen. So to multiply or turn moles into volume at STP of a gas, we're going to multiply by 22.4 liters for every 1 mole of O2. All right, and so then we're going to multiply those through. 403 times 6 times 22.4, and we're going to divide by 180. And we get 300.9, which I guess rounds to 301. 301 liters of oxygen. All right. So moving on, got another question here. This one is also similar in some way, and it's different to another. So question 4A, we need a balanced reaction. Before we do that, notice we're not actually given a reaction for question 4. So we're going to read it carefully and see if we get any clues so we can help use those to write our reaction ourselves. So we got Sam's Bentley, and her engine burns octane, which is fancy. And it burns it in a combustion reaction. Okay. She burns 30 liters of a tank of gas. Okay. 30 liters of gas, octane gas, I suppose. And the density of octane is incorrect. It is 703 grams per liter, or 0.703 kilograms per liter. And that's probably important, so we should probably highlight that. Density of octane. And how many grams of CO2 will she produce? How many grams of CO2 will she produce? All right. So we want to know how much carbon dioxide Sam's going to produce out of her tailpipe, and specifically what it would weigh. All right, so let's find out. So to do that, we have to, we were given some clue for a reaction. We know that we're going to be burning octane. And we know it is a combustion reaction, a burning reaction, like a typical burning reaction. So that means we're going to be adding oxygen to this reaction. And in the process, we're going to be making some new stuff. Now, combustion reactions, just like what you breathe out, because you breathe in oxygen, we do. We've got to breathe out carbon dioxide. And the other product of a combustion reaction is water. As you saw up here, we're talking about yeast. Okay. I can already see this is going to be a pain to balance, so let's just dig into it, shall we? So let's start with, we've got 8 carbons here, so we'll put 8 here. And hydrogens, we've got 12 here, so we'll put a 6 there. Oh, maybe this isn't going to be so bad after all. Okay, cool. Now for oxygens, I can count 8 times 2, that's 16 oxygens here, so 16 oxygens plus 6 oxygens. So in total, we have 22 oxygens. So we need 22 oxygens here, so I'm going to put an 11 there. Okay, so there's a balanced reaction. Now, we're going to move on. We're going to convert. So now we know Sam has 30 liters of octane. 8H18. Okay. And we know the density of octane. So we can say we can convert that into a number of grams of octane over 1 liter of octane. So that's to cancel out the volume and turn it into how much it'll weigh. We're turning that into a weight. Next, we need to go to the mole bridge. We need to convert things into moles. So we need to find the molar mass of octane. Okay, great. So the molar mass of octane, C8H18, means we'll have 8 times 12.0 for carbon, so that'll be 96.0 grams per mole. And then hydrogen is going to be 18 times 1.0, which is 18.0 grams per mole. And when we add those together, what do we get? We get 116.0 grams per mole. No, we get 114. Wait, what do we get? Ah, God, tired. 96 plus 18, 114. Okay. So 1 mole of C8H18 gives us 114.0 grams per mole. No, grams. C8H18 octane. And now we need to convert that into what are we doing? We're asking how much carbon dioxide sounds like. Okay, so we're going to convert moles of octane to moles of carbon dioxide. It says that 8 moles of carbon dioxide for every 1 mole of octane. C8H12. And lastly, we want to know turn that into a mass, not the number of moles. So let's cancel out all the units that cancel here diagonally. Now we have moles of carbon dioxide, so we know that 1 mole of CO2 is going to give us, so the molar mass of CO2 is 1 times 12.0, which is 12.0 grams per mole. And 2 oxygens is 2 times 16.0, which is 32.0 grams per mole. All right, so that means when we add these together, we get 44.0 grams per mole. So we're going to multiply by 44.0 grams of carbon dioxide. All right, so we're going to find out how much all this weighs. So 30 times 703 times 8 times 44. And we're going to divide that by 114. It's going to give us 65 grams of, wait, hang on, how many sig figs did I get here? I only give 1 sig fig. Great, so we're going to round that to 1, so 70,000 grams. So we should call that 70,000 grams of CO2. But we should also add, we should turn that into kilograms. That's like 70 kilograms of carbon dioxide. Does that sound right? Well, I guess it's heavier than the octane probably was. She only had 30 liters of octane. But then we're bringing in a lot of oxygen to combine with it. So I guess it does sort of add up a little bit. Okay, so 70 kilograms of carbon dioxide. Crazy. All right, last question. So this is a famous reaction, the Haber process. We talked about it a little bit in class, but we'll talk about it more later. All right, so Haber process changes the nitrogen in the air into ammonia for fertilizer. World's most performed industrial chemical reaction. All right, so how much hydrogen gas, determine how much hydrogen gas we'll need in liters to produce 50 kilograms of ammonia. All right, so just like any other question, first thing we're going to do is we are going to balance this reaction. So we'll write the reaction out. and then we'll balance it. So I've got 2 nitrogens here and only 1 here, so I'll put a 2 there. That made 6 hydrogens in total, so I need a 3 here, and then I've balanced it. All right. So next step is we're going to figure out how much hydrogen gas we need. If we have 50, we want to make 50 kilograms of ammonia. So let's start with 50. Let's start down here. 50 kilograms of ammonia. All right, now we dealt with ammonia in an earlier example. You don't have to memorize it, but it's probably easy to find that ammonia has a molar mass of ammonia equals 17.0 grams per mole. Okay, so we'll use that. And, oh, we got kilograms of ammonia. So first we'll turn that into grams, okay? So 1,000 grams for every 1 kilogram. That cancels out kilograms of ammonia, of course. Okay, now we're going to use the molar mass here. It says 1 mole of ammonia is equal to 17.0 grams of ammonia. And now we're going to use this conversion factor to make a conclusion about how much hydrogen gas we need to make, because it's hard to make hydrogen gas. So this says that 2 moles of ammonia can be made from 3 moles of H2, hydrogen gas. And lastly, we want to know how many liters of hydrogen gas, so we're going to convert that using our molar volume of at STP, so 22.4 liters. And if you don't see STP written in the question, we should assume standard temperature and pressure. So we get 22.4 liters of hydrogen for every 1 mole of hydrogen. All right, so what does that give us? Cancel out these guys just to make sure that everything cancels. And we'll just crunch the numbers here. 50 times 1,000 times 3. I'm just multiplying the tops together. Times 22.4. It's a lot. Then we'll divide it by 17. Then we'll divide it by 2. Wow, okay. So we need a lot of liters. So we're going to round that to 100,000 liters of H2 at standard temperature and pressure. All right. So let me know if you have any questions about that, and maybe we can meet in Flex on Monday. Good luck with your studying, and I will see you guys next week.